So the device I'm going to explain today is called the Peltier cooler, and we're gonna demo it for you. So a Peltier cooler is basically a type of thermoelectric cooler for MEMS or semiconductor devices, that kind of things. So we have a hot side and a cold side, and we want to take heat from cold to the hot side, which wouldn't happen normally, right? So normally they would try to become equivalent, and heat would go from this side to this side. So basically, the device is rather simple. We have a N-type semiconductor here and a P-type here, and we have a current flowing through it. That's all it is. So you can see the geometry we have created here using OFLE. Okay, so when we can go here and it can explain to you the various parts. So in the analysis data module, as I explained, you set the various maybe boundary conditions or material properties, that kind of thing. So we have the P-type semiconductor on this side, N-type on this side, and we have a bunch of copper plates. And we also set the boundary conditions. So normal current density here, and then we have the mechanical clamping down here, potential prescribed on this side, and a temperature set here. So we're gonna find the values throughout the device based on these boundary conditions. Okay, so we have also created a mesh here. This is the mesh that we have created. Okay. Yeah, so the mesh was generated inside the software, but you can import it if that's something you want to take it here from some other place. So you can actually do the same with the geometry you want. Okay, so let me hide these, and you can also view the mesh like this if you want. Okay, so let me hide these and go to the solver module. Here you can do like the setting for the solver, basically what kind of solver you want to use, iteration, convergence criteria, ambient temperature, whatever else you want to change. Depending on the problem, the menu would be different, of course. Yeah, and then you run the simulation here. Okay. So for the results, we've selected a few things here. We have the temperature throughout, so you can see it starts from like 20 degrees and it goes to negative 40 almost on this side. So it's cooling definitely. Even though, if you remember from the ambient temperature that we set, sorry, this one, we set the ambient temperature to basically zero. So, okay. Sorry. Okay. And we have the nodal displacement. So you can see due to the temperature gradient, there will be some shrinking in some parts. And again, I mentioned in other videos also, but remember that this is a normalized shrinking, basically displacement. So the values are not true values, but the ratio of displacement is true. So for example, if this is the maximum displacement and this is half, that is the true value. Because otherwise maybe the shrinking is not too much, so you cannot view it. That's why we show it like this. Okay, and we have the electric potential throughout the device here, as well as current density. So yeah, we have decided to show with vector. Of course, for any of these, you can change the how you show it. Yeah, for example, like this, or yeah, you have to just see what options are available depending on the thing you're showing. It can be different. Okay. Thank you.